Welcome. Thank you for joining us here at the Z-Files. What follows is a journey beneath the surface of Mars, where no human has ever stood. And yet it could be the most hospitable space on the entire planet. It is dark, quiet, ancient, and formed by rivers of lava that flowed and then drained away billions of years ago. What remains are long, cathedral-like tunnels, waiting in silence. Let yourself settle now, and we will go down together, slowly, into the underground world that may one day become humanity's first true home away from Earth. Part 1. The deadly surface of Mars. To understand why anyone would want to live underground on Mars, you first have to spend a little time on the surface. Not long. Just long enough to feel the weight of what is up there, waiting. The surface of Mars is not simply cold or remote in the way that Antarctica is cold and remote. Antarctica, for all its harshness, is still wrapped in the same magnetic field that covers every corner of Earth. It still sits beneath an atmosphere thick enough to scatter ultraviolet light. The surface of Mars has neither of those protections in any meaningful degree, and the result is an environment that is hostile to biology in ways that are quiet and cumulative rather than immediately violent. That quietness is part of what makes it so important to understand. Start with radiation. Mars has no global magnetic field in the way Earth does. Earth's magnetosphere is generated by the movement of liquid iron in its outer core, and it deflects a vast portion of the charged particles streaming outward from the Sun. Mars, by contrast, lost most of its global magnetic field billions of years ago. What remains are localized patches of magnetism preserved in certain ancient rocks in the southern hemisphere. Relics of a time when the planet may have had a functioning dynamo of its own. But those patches do not form a coherent protective shell. They are irregular and scattered, like pieces of an old shield that has long since fallen apart. Without that shield, the Martian surface is exposed to two overlapping streams of radiation. The first is solar energetic particles, which are bursts of high-energy protons and electrons thrown outward by the Sun during solar flares and coronal mass ejections. These events happen unpredictably and can deliver a sharp, intense dose of radiation to anything on the surface within hours of the eruption. The second stream is galactic cosmic rays, which arrive from outside our solar system entirely. These are particles that have been accelerated to extraordinary speeds by ancient stellar explosions, and they drift through interstellar space in all directions before arriving at Mars with the quiet persistence of background noise. Unlike solar events, galactic cosmic rays are essentially constant. They press against the surface of Mars every single second of every single day. Earth's atmosphere helps block galactic cosmic rays. The column of air above any point on Earth's surface is thick enough to absorb and scatter much of this radiation before it reaches the ground. Mars has an atmosphere, but it is thin, approximately 1% of Earth's atmospheric pressure at the surface. That sliver of carbon dioxide offers only a modest shield, and measurements taken by the Curiosity rover's radiation assessment detector confirmed what scientists had predicted. The surface radiation environment on Mars is significantly more intense than what humans routinely experience on Earth. Estimates suggest that a person living on the Martian surface without heavy shielding would receive a radiation dose many times the annual limit considered acceptable for radiation workers on Earth, and this would accumulate year after year. Long-term exposure to that kind of radiation is associated with elevated cancer risk, potential damage to the central nervous system, and harm to the lens of the eye. There is also growing concern about what high-energy particles may do to cognitive function over time. Some studies conducted in the context of space medicine, using particle accelerators to simulate cosmic ray exposure in animal models, have found effects on memory and behavior that researchers describe as concerning. These are not instant, catastrophic injuries. They are slow, invisible, and deeply relevant to the question of whether humans can sustainably live on the Martian surface over the years and decades required to build a real civilization. Then there is the cold. Mars is, on average, far colder than Earth. Average surface temperatures sit somewhere around -60°C, though this varies considerably by latitude and season. Near the equator, on a clear afternoon when the thin sun is highest, temperatures can briefly rise above freezing. But by the middle of the night, the same location may plunge to -70 or even colder. This daily swing is extreme. The Martian atmosphere is too thin to hold heat the way Earth's does, so warmth absorbed during the day bleeds away rapidly once the sun sets. The result is a diurnal temperature range, meaning the difference between daily high and nightly low, that can exceed 80 or even 100 degrees Celsius in some locations. For engineering, this is deeply challenging. Repeated thermal cycling, the expansion and contraction of materials as they heat and cool each day, creates structural stress. Seals, joints, and surface-built habitat walls all experience this stress cycle again and again, month after month. Materials that work well under steady, mild conditions can crack or fail under sustained thermal cycling at Martian extremes. Any structure built on the surface must be engineered to survive not just one cold night but thousands of them over a mission lifespan of years. For human biology, the cold matters in a different way. Maintaining body temperature in an environment of -60 requires constant energy expenditure by life support systems. Thermal insulation must be extreme. A breach in any part of the system, even a small one, is immediately dangerous. Cold of that magnitude does not leave room for error. But perhaps the subtler and in some ways more insidious challenge of the Martian surface is what it does to time. Mars has a day that is close to Earth's in length, just over 24 hours and 37 minutes, and this is often presented as a kind of lucky coincidence. And in a narrow sense it is. Human beings have a circadian rhythm, an internal biological clock, that runs on roughly a 24-hour cycle, and Mars's solar length falls within what researchers believe is the range the human body can entrain to without severe disruption. Early mission simulations, where participants lived on Martian time inside controlled facilities on Earth, found that people could adapt to the slightly longer day without catastrophic difficulty, though some individuals adjusted more easily than others. The deeper problem is not the length of the Martian day but the quality of Martian light. The sun as seen from Mars is smaller and dimmer than from Earth. Mars is roughly 1.5 times farther from the sun than Earth is, and the inverse square law of light intensity means the Martian surface receives substantially less solar energy. The light that does arrive is also filtered differently by that thin atmosphere, giving it a quality and color that is not quite what human eyes evolved to receive. The circadian system relies heavily on light, specifically on the blue wavelength component of light, to set and reset the internal clock each day. Bright, blue-rich light in the early part of the active period helps suppress melatonin and promote alertness. Dim, warm-toned light in the late period allows melatonin to rise and sleep to come. On the Martian surface, achieving the right quality and intensity of light at the right times would require active engineering. Habitats would need to supplement or entirely replace natural light with artificial systems calibrated to the circadian biology of their inhabitants. Relying on windows alone would likely be insufficient. And if those lighting systems failed, or if schedules drifted out of alignment, sleep quality would degrade, cognitive performance would follow, and the cascade of effects that poor sleep sets in motion, reduced immune function, impaired judgment, emotional dysregulation, would begin to compound over time in ways that mission planners consider a serious risk. There is also dust. Mars is prone to dust storms, some of which grow to cover the entire planet for weeks at a time. During a global dust storm, sunlight at the surface can be reduced dramatically, not just dimming the already weak Martian sun but potentially cutting it to a fraction of its normal value. Solar panels become less effective. Any reliance on natural light becomes essentially impossible. Dust also coats surfaces, infiltrates mechanical systems, and carries the potential for chemical irritation if inhaled. Martian regolith, the loose surface material, contains perchlorates, a class of chemical compounds that are toxic to humans at sufficient exposure levels. Dust management is not a minor inconvenience on Mars. It is an ongoing, serious concern. All of these factors together, radiation, temperature swings, poor light quality, dust, and the fragility of surface structures, form the context in which scientists and engineers have begun to think seriously about going underground. Not as a fallback or a last resort, but as a primary strategy. The surface is where you land. It is where you begin. But it may not be where you live, not if you intend to stay for a very long time. There is something quietly clarifying about understanding all of this. The challenge of Mars is not the drama of impact craters or thin air alone. It is the patient, daily accumulation of hazards that no engineering patch can fully overcome on the surface. The solution, when you see it, feels almost inevitable. You go down into the ancient quiet of the rock itself. And the rock of Mars has something waiting for you. Something that formed long before humans existed, long before Earth held any complex life at all. Something vast and dark and, in its own way, welcoming. Part 2. The Architecture of Martian Silence. There is a kind of tunnel on Mars that was not made by any machine or any living thing. It was made by fire, or rather by the absence of fire, by the moment when a river of flowing lava lost its roof and drained away, leaving behind a hollow tube of cooled rock. These structures are called lava tubes, and they exist on Earth as well, where they can be explored on foot in places like Hawaii, the Canary Islands, and Iceland. But the lava tubes of Mars are thought to be something else entirely. Something larger, older, and stranger than anything their terrestrial counterparts have prepared us to imagine. To understand a lava tube, you need to picture how lava flows work. When a volcano erupts and sends molten rock moving across a landscape, the outer edges of the flow cool first. They cool because they are in contact with the air, and even thin air carries heat away from a surface over time. As the outer shell of the flow hardens into solid rock, it forms a kind of insulating crust. Inside that crust, the lava continues to move, channeled now by the hardened walls around it. The interior keeps flowing, sometimes for great distances, while the outer surface looks almost still. When the eruption eventually slows and the supply of molten rock from the source diminishes, the interior lava drains away. What remains is a hollow tube, with walls and ceiling made of cooled basalt and a floor that may be rough with solidified lava or smooth where the last thin flow coated everything before hardening. On Earth, lava tubes can be impressive. Some Hawaiian tubes are large enough to walk through without stooping. But Earth's gravity is strong. The weight of rock pushes downward with force, and this limits how wide a lava tube ceiling can be before it collapses under its own mass. There is a ceiling to size, in the most literal sense. Mars has lower gravity, roughly 38% of Earth's. This single fact changes everything about what a lava tube can be on that planet. A ceiling that would collapse on Earth under its own weight can remain stable on Mars because the downward gravitational pull on every kilogram of rock is so much weaker. Computer models and theoretical analyses, developed by researchers at a range of institutions over the past decade and a half, suggest that Martian lava tubes could be enormous. Not just bigger than their Hawaiian counterparts, but potentially orders of magnitude larger. Some estimates suggest that the widest Martian lava tubes could have vaulted ceilings reaching 1 kilometer above the floor, with widths to match. Others are more conservative, but even the conservative estimates describe structures far beyond anything accessible on Earth. Evidence for these structures has been accumulating from orbit. Mars is dotted with features called pits, which are essentially skylights, places where the ceiling of a subsurface cavity has collapsed in a rough circle, leaving a hole that opens downward into darkness below. Images from orbiting spacecraft, including those from the Mars Reconnaissance Orbiter, have captured these pits in remarkable detail. Photographs show sheer walls dropping into shadows that the cameras can barely penetrate. In some images, the sun angle is sufficient to illuminate the floor of the pit partially, and what can be seen suggests a wide, level interior that extends beyond the edges of the image. These pits are scattered across volcanic regions of Mars, particularly in areas like the Tharsis Plateau, which hosts the largest volcanoes in the solar system, and around the Elysium volcanic province. The Tharsis region is relevant here in a specific way. It is home to Olympus Mons, the tallest volcano in the solar system, which rises approximately 22 kilometers above the surrounding plains. The volcanic history of Tharsis is ancient and vast, with eruptions that likely continued intermittently for billions of years. All of that volcanic activity means all of that lava flow, and all of that lava flow means the potential for an extraordinary network of tubes beneath the surface. Whether these tubes are intact, partially collapsed, or fully accessible remains unknown. No mission has yet descended into one. But the orbital evidence is consistent with their existence in substantial numbers. There is an intriguing and somewhat sobering detail about the timescale here. The volcanic activity on Mars that likely formed these tubes peaked billions of years ago. The tubes themselves are therefore ancient, shaped by a world that was geologically and perhaps even climatically different from Mars today. Mars in its earlier history may have had a denser atmosphere, liquid water at the surface, and a more active internal heat engine. The lava tubes formed in that earlier era and have been sitting in the dark ever since, preserved by the stillness of a geologically quieter planet. Rock is a patient material. In the absence of erosion by water or wind at depth, these structures may have survived largely intact across billions of years. What a lava tube offers, beyond its remarkable size, is thermal stability. The key is thermal mass. Rock is slow to change temperature. The surface of Mars swings wildly between day and night, gaining and losing heat in that dramatic diurnal cycle described earlier. But a few meters below the surface, rock insulates. And deep inside a lava tube, with meters of rock overhead, the temperature is no longer governed by the surface cycle at all. It is governed instead by the deep thermal equilibrium of the planet itself. Estimates of what this temperature might be inside a Martian lava tube vary, but current modeling suggests something in the range of -20 to -30 degrees Celsius, or possibly somewhat different in tubes near the poles versus the equator. These are cold temperatures by human standards, and they would still require heating. But they are stable. They do not swing by 80 or 100 degrees every sol. A habitat inside such a tube could be heated to a comfortable range and maintained there with far less energy than a surface structure fighting a daily temperature war with the environment. The acoustic properties of a large, curved rock chamber deserve a moment of attention too, because they connect in a quiet way to the experience of living inside one. Large stone chambers, whether natural caves or ancient cathedrals built from stone, have distinctive acoustic qualities. Sound reflects off curved walls, spreads through open space, and arrives at the ear softened and blended with its own echoes. In certain dimensions, this creates a reverberance that humans often describe as peaceful or even sacred. Smaller sounds become part of the ambient texture rather than sharp intrusions. A large Martian lava tube, by virtue of its size and composition, would likely produce a similar effect. The crack of a tool falling to the floor would echo and diminish before it could startle. The hum of life support equipment might blend into a low, steady presence rather than a sharp mechanical noise. This is not a trivial consideration for people who must live in that space for months or years. The acoustic environment shapes mood, alertness, and the sense of ease or unease in a profound way that is easy to underestimate until you have spent time in a space that gets it wrong. The darkness of a lava tube is also worth sitting with as a concept. Away from any artificial light source, a sealed underground chamber on Mars would be completely and absolutely dark. Not the partial darkness of a room with a window, or even the near darkness of a rural night. Total darkness, the kind that makes vision entirely useless. This might sound alarming, and in an uncontrolled way it would be. Disorientation in complete darkness can be severe. Spatial awareness collapses. The sense of time dissolves. But in a controlled habitat, with every light source being artificial and therefore adjustable, this darkness becomes an extraordinary asset. It means the light environment is entirely in the hands of the people who live there. They can create whatever light they need, in whatever spectrum and intensity suits the moment. And when it is time for sleep, they can create darkness that is more complete and more perfectly calibrated to biological need than anything achievable on the surface of Mars or, arguably, anywhere on Earth outside of a purpose-built sleep chamber. There is something in that idea that is worth letting settle. The most controllable sleep environment on Mars may not be a high-technology dome bristling with sensors and regulators. It may be a cave. An old one, shaped by forces that had nothing to do with human intention, that has been sitting in the dark for billions of years, waiting. The rock overhead has a thickness to it, not just physically but conceptually. Beneath those meters of basalt, a person is shielded from radiation in a way that no surface construction can replicate without enormous mass. Rock is among the most effective radiation shielding materials available, precisely because of its density and the way it scatters and absorbs high-energy particles. Even a few meters of solid basalt overhead would reduce the radiation dose inside the tube to something significantly closer to Earth's surface background. Deeper rock would reduce it further. The very walls of the tube, formed by ancient volcanic activity without any thought of human habitation, happen to provide the kind of mass shielding that would take enormous resources to replicate artificially on the surface. This is the quiet and slightly astonishing thing about Martian lava tubes as habitats. They solve, in a single architectural gift, several of the most serious problems that make the Martian surface so dangerous. Radiation shielding through rock mass. Thermal stability through thermal mass and depth. Light control through complete enclosure. Structural protection from dust storms, micrometeorites, and the daily mechanical stress of temperature cycling. And vast interior volume, potentially enough to house not a small research outpost but something beginning to resemble a town, or eventually something much larger than that. We do not yet know the precise layout, condition, or accessibility of any specific Martian lava tube. No rover has descended into one. No drill has reached one from above. What we have are orbital images, theoretical models, and the analogy of terrestrial tubes scaled upward through the lens of Martian gravity. But the evidence is consistent. The logic is sound. And the scale of what may be waiting beneath the surface of Mars is, by any reasonable estimate, extraordinary. Something immense and dark and very old has been there for billions of years. And it may be precisely what we need. We have spent time now on the surface and then descended into the rock itself. The next step is to understand the living thing that will one day inhabit these spaces, and specifically what happens to it when the rhythms of light and dark, of waking and sleeping, are taken away or given back in new forms. The story of the human body's relationship to darkness is older than history, and it will shape everything about how we build our homes beneath the Martian surface. Part 3. The biological need for darkness. The human body keeps time, not with thought, not with intention, but with chemistry. Deep inside the brain, a cluster of neurons called the suprachiasmatic nucleus acts as a master clock, coordinating the rise and fall of hormones, body temperature, digestion, and alertness across a roughly 24-hour cycle. This system is called the circadian rhythm, from the Latin for about a day, and it is ancient. Single-celled organisms have versions of it. It evolved long before eyes did, tracking the planet's rotation through chemical signals rather than light. But in humans, light is the primary synchronizer. Specialized cells in the retina, distinct from the rods and cones used for ordinary vision, detect blue wavelength light and send that information directly to the master clock. Bright light in the early active period suppresses melatonin, the hormone associated with sleepiness, and holds the body in an alert, wakeful state. As light dims in the later part of the day, melatonin rises, body temperature drops slightly, and the drive towards sleep builds. Remove that light signal, or distort it, and the clock begins to drift. Astronauts know this problem well. On the International Space Station, the sun rises and sets every 90 minutes as the station orbits Earth. Without careful management of artificial lighting schedules and blackout sleeping quarters, sleep quality degrades significantly. Studies of ISS crews have found that many astronauts sleep fewer hours than recommended and report poorer sleep quality over time. Cognitive performance, reaction time, and emotional regulation all show measurable declines linked to disrupted sleep in long-duration spaceflight. Analog missions on Earth, where crews live in isolated, enclosed environments designed to simulate planetary habitats, reinforce this picture. Participants in the HIC's missions in Hawaii and the Mars 500 isolation study in Moscow both reported sleep disturbances, mood shifts, and the subtle cognitive erosion that accumulates when the body's internal clock loses its anchoring signal. In several cases, the culprit was identified not as stress alone but as the absence of well-controlled light. The body is looking for a signal. When it cannot find one, it begins to lose its sense of where it is in time. This is where the lava tube becomes unexpectedly relevant to sleep science. A sealed underground habitat has no ambient light. There is no Martian dawn leaking through a window, no dim glow from a dust-filtered sky. The light environment is entirely artificial and entirely controllable. Engineers and chronobiologists, scientists who study biological time, could design a lighting system calibrated precisely to the needs of each inhabitant. Blue-rich, high-intensity light in the morning period to anchor the clock. Gradually warming, dimming light in the hours before sleep. And then, when it is time to rest, a darkness more complete than anything available on the surface. That kind of darkness matters. Even small amounts of light during sleep, a status light on a device, a faint glow under a door, are associated with shallower sleep and more frequent waking. In a lava tube habitat with no external light source, sleeping quarters could be made genuinely, completely dark with minimal effort. No blackout curtains required. No light-blocking technology fighting against an ambient environment. Just the rock, and the dark it naturally holds. There is also the matter of the Martian soul length. At 24 hours and 37 minutes, a Martian day is close to but not identical to Earth's. Research on human circadian flexibility suggests most people can entrain, meaning synchronize their clock, to cycles in the range of roughly 23.5 to 25 hours. A Martian soul falls within that range for most individuals, which means a well-managed lighting schedule inside a lava tube habitat could plausibly keep circadian rhythms aligned without the need to force the body onto an artificial Earth day cycle. Crews could live on Mars time, supported by light cues designed for Mars. None of this is guaranteed, and individual variation is real. Some people adapt more easily than others. Long missions will require monitoring, adjustment, and probably personalized schedules for different crew members. But the tools exist, and a lava tube habitat provides a physical environment in which those tools can be most effective. The darkness is not a problem to be solved. It is, in a quiet way, the solution itself. We understand now what the body needs from its environment in order to rest. The next question is how designers and engineers are beginning to imagine the spaces where that rest will happen, and how a cold, ancient rock tunnel might be transformed into something that feels, against all expectation, like home. Part 4. Engineering the Subterranean Dreamscape. Knowing that a lava tube offers the right conditions for human habitation is one thing. Turning a cold basalt tunnel into a place where people can actually live, sleep, and maintain their well-being over years is something else entirely. Engineers, architects, and space habitat designers have been working on this problem in overlapping ways. And while no Martian underground habitat has been built, the conceptual frameworks are taking shape with increasing detail and seriousness. The first challenge is atmosphere. A raw lava tube on Mars contains the same near vacuum of the Martian surface atmosphere, roughly 1% of Earth's pressure, composed mostly of carbon dioxide. Before anyone can step inside without a pressure suit, the tube must be sealed and pressurized. The conceptual approach most discussed involves inflatable or modular pressure liners, essentially large, airtight structures that conform to the interior shape of the tube and hold breathable atmosphere inside. Think of a long, inflatable sleeve fitted within the rock channel, anchored at key points, and pressurized to comfortable levels. The rock walls outside the liner serve as structural support and radiation shielding. The liner itself handles the atmospheric boundary. Once pressurized and heated, the interior space becomes workable. Modular habitat units, designed for transport from Earth and assembly inside the tube, would divide the interior into functional zones. Sleeping quarters would be intentionally small and enclosed, not because space is limited in a large tube, but because smaller sleeping spaces are psychologically easier to make dark, quiet, and thermally stable. Research on sleep environment preferences consistently shows that people sleep better in spaces that feel contained and sheltered rather than open and exposed. Lighting systems in these quarters would be the heart of the circadian management strategy. LED arrays capable of shifting across the full visible spectrum, from cool blue-white in the morning to warm amber in the evening, have already been deployed on the International Space Station as part of ongoing efforts to improve crew sleep. For a Mars habitat, similar systems would be standard. Some proposals go further, describing ceiling panels that simulate a gradual sunrise, brightening slowly over 20 to 30 minutes to ease the transition from sleep rather than snapping the brain into alertness with sudden light. The reverse process at day's end, a slow dimming that mirrors a natural sunset, would allow melatonin to rise naturally and sleep to come without pharmaceutical assistance. Beyond sleeping quarters, the larger habitat volume offers possibilities that a cramped surface module cannot. Green walls, vertical hydroponic systems growing food plants under supplemental lighting, would serve multiple functions simultaneously. They would produce food, scrub carbon dioxide from the air through photosynthesis, add humidity to what would otherwise be a very dry pressurized environment, and provide the psychological benefit of living greenery. Studies of confined environment psychology consistently identify contact with plants as a meaningful contributor to mood and perceived well-being. In a place where the view outside is either solid rock or, through a camera feed, a cold orange desert, a wall of growing things carries significant weight. Acoustic design would shape the feel of the space in ways that are easy to overlook but deeply important. The natural reverberance of a large rock chamber can be managed with soft materials, fabric partitions, plant walls, and careful geometry to create spaces that feel calm rather than echoing and disorienting. Sleeping quarters especially would be acoustically isolated, using mass and absorbent materials to bring background noise to the low levels associated with deep, restorative sleep. Water recovery and air circulation systems would hum quietly in service spaces, kept physically separate from living and sleeping areas to minimize noise intrusion. Thermal management would use the natural cold of the rock as a passive heat sink for electronics and equipment, while heating systems keep living areas comfortably warm. The rock itself becomes a partner in the engineering rather than an obstacle. None of these proposals are science fiction. Each component, inflatable liners, circadian lighting, hydroponics, acoustic treatment, draws on technology that either exists now or is in active development for near-term space missions. The integration of all of them into a coherent underground habitat is the engineering challenge, and it is a serious one, but it is a challenge of coordination and logistics rather than a fundamental physical possibility. What is being imagined, in careful and growing detail, is a place where a person can close their eyes at the end of a long day on Mars and sleep well. That is a simple goal, and it is not simple to achieve. But in the dark, insulated quiet of an ancient lava tube, it may be more achievable than anywhere else on that planet. The habitat itself is only the beginning, though. A place where a handful of researchers can sleep soundly is a remarkable thing. But the longer vision, the one that some engineers and planners are already sketching out, is something far larger. Part 5. Scaling the Underworld Civilization. A single pressurized sleeve inside a Martian lava tube would be an outpost. A cluster of interconnected modules would be a base. But the tubes themselves, if the largest estimates are close to correct, are not sized for outposts or bases. They are sized for cities. That is not hyperbole. It is a straightforward consequence of the numbers. If some Martian lava tubes truly have interior widths and heights on the scale of hundreds of meters or more, then the enclosed volume of a single tube could rival or exceed the usable floor area of a small city. Early human settlements would occupy a tiny fraction of that space. The rest would sit in reserve, available for expansion as population grows and infrastructure develops, without requiring any new excavation or surface construction. The shell is already there. It formed billions of years ago and has been waiting in the dark. Growth from a small research outpost to something resembling a functioning community would require solving problems in roughly the order that any frontier settlement has faced throughout human history: food, water, energy, shelter, and then, once survival is assured, the social and psychological architecture of daily life. Underground on Mars, each of these problems has a specific character. Food production in a sealed underground habitat would depend on hydroponics and controlled environment agriculture. Without natural sunlight, all plant growth would require artificial lighting, which demands energy. But the efficiency of modern hydroponic systems is remarkable. Crop yields per square meter under optimized LED lighting and nutrient delivery can exceed what traditional field agriculture achieves by substantial margins. A relatively modest growing area, carefully managed, could provide a meaningful portion of the caloric and nutritional needs of a small community, supplemented by supplies from Earth in the early phases and increasingly self-sufficient over time. Water, in a lava tube settlement, might be sourced from multiple directions. Mars has water ice in its polar regions and in subsurface deposits that radar data from orbiting spacecraft have mapped in increasing detail. Water extracted from the regolith or ice deposits and purified would be a critical resource. Closed-loop water recycling, already practiced extensively on the International Space Station, would minimize loss. Over time, a lava tube settlement might develop local water systems of modest but real sufficiency. Energy is perhaps the most complex dependency. Solar power on the surface is feasible but limited by dust accumulation and seasonal variation. For an underground settlement, Surface solar arrays connected by cable to the subterranean habitat could provide baseline power. Nuclear fission reactors, compact designs developed for space applications, are a widely discussed alternative that would offer reliable, continuous power independent of surface conditions. A growing settlement would likely use both, with redundancy built in at every stage. The psychological dimension of scaling matters as much as the physical one. There is substantial research, drawn from analog environments including polar research stations, submarines, and long-duration space simulations, showing that small isolated groups face predictable social stresses over time. Interpersonal conflict, authority tension, and monotony are consistent findings. As a community grows beyond a small crew towards something larger, these dynamics shift. More people means more social diversity, more division of labor, more opportunities for the kind of informal interaction that sustains mood and cohesion. A community of 50 functions differently from a crew of 6, and a community of 500 differently still. Urban planning for underground Mars would be a genuinely new discipline, drawing on everything known about how physical space shapes human behavior. Wide communal corridors that encourage casual encounter. Quiet residential zones buffered from noisy work areas. Communal gardens and green spaces providing the psychological equivalent of parks. Spaces for gathering, for solitude, for work, and for rest, each designed with the particular constraints and gifts of the underground environment in mind. Sleep, within this growing civilization, would remain a central design consideration. As any community expands, managing light schedules, noise, and circadian alignment becomes more complex. Shift work may develop as the settlement requires continuous operation. Chronobiologists working with habitat designers would need to ensure that the systems supporting healthy sleep scale alongside population. That is a solvable problem, but it must be planned for rather than discovered after the fact. What is being imagined here, in the careful language of engineers and scientists, is something genuinely unprecedented. A civilization that begins underground, that grows into the ancient architecture of a volcanic world, and that builds its daily rhythms, including its rhythms of waking and sleep, from scratch. The darkness that surrounds it is not a limitation. It is, in a very real sense, the foundation. Part 6. Water, ice, and the hidden ocean beneath. Mars is often described as a desert world, and in one sense that is accurate. Liquid water on the surface today is essentially absent. The combination of low atmospheric pressure and cold temperatures means that water exposed at the surface would either freeze or sublimate directly into vapor without passing through a liquid phase in most conditions. For a long time, this led to the assumption that Mars was simply dry, a cold and desiccated world where water existed only as a memory locked in ancient geology. That picture has changed considerably over the past 2 decades. Mars is not dry. It is cold, which is a different thing entirely. Water ice sits in abundance at the Martian poles, visible from orbit in the layered deposits of the polar caps. The North Polar Cap in particular contains a significant reservoir of water ice beneath a seasonal covering of carbon dioxide frost. Radar instruments aboard orbiting spacecraft have probed beneath the surface and found evidence of subsurface ice deposits at a range of latitudes, not just at the poles. Some of these deposits appear to be relatively shallow, within a few meters of the surface in certain regions. Others are deeper. The picture that has emerged from years of orbital data is of a planet with substantial water resources distributed across its body, locked in ice and bound into minerals, waiting to be accessed. More provocative still are the radar-based detections of what some researchers have interpreted as liquid water beneath the southern polar ice cap, likely kept liquid by dissolved salts that lower the freezing point significantly, and possibly by residual geothermal heat. These findings remain debated, and the evidence is not universally accepted, but even the conservative interpretation of the data acknowledges that subsurface brines, water made liquid by dissolved minerals and salts, may exist somewhere beneath the Martian surface. For a lava tube settlement, the most practically relevant water sources are the ice deposits. Extracting water from ice-bearing regolith is a process that researchers and engineers have studied in considerable detail. The basic approach involves heating the soil to drive off water vapor, then condensing and purifying it. This is energy-intensive but technically straightforward. A settlement with sufficient power, whether from solar arrays, nuclear reactors, or a combination of both, could mine water from the surrounding environment rather than depending entirely on supplies launched from Earth. This matters for sleep and daily life in a specific way that is easy to overlook. Water is not only for drinking and hygiene. It is an excellent radiation shielding material, because hydrogen atoms are particularly effective at absorbing and scattering the energetic particles produced by cosmic rays. A habitat whose walls incorporate water-filled panels or bladders would have enhanced radiation protection beyond what the rock overhead already provides. Water sourced locally and used architecturally as shielding would be among the more elegant solutions available to habitat designers, a material that serves simultaneously as life support resource, thermal mass, and radiation barrier. Water also makes agriculture possible, and agriculture makes psychological comfort possible in ways that go beyond nutrition. Growing food in an enclosed space creates a cycle of tending, observing, and harvesting that provides structure to daily life. It creates the satisfaction of visible growth in an environment where very little changes on its own. It connects people to a biological rhythm that is older than civilization. For a community living in permanent artificial light beneath kilometers of Martian rock, that connection matters more than it might seem. The water cycle of a sealed habitat would be closed almost entirely. Water consumed would be recovered from breath, urine, and wastewater through systems already proven on the International Space Station. Over time, losses would be made up from local extraction. A mature settlement could conceivably run a nearly closed water loop, extracting only what it needs to replace genuine losses, which would be small. This degree of self-sufficiency would reduce dependency on Earth resupply, which, given the communication delays and launch windows governing Mars missions, is not a convenience but a survival consideration. The presence of water, ice or otherwise, also shapes the question of where specifically on Mars to locate a lava tube settlement. Tubes in regions with accessible subsurface ice deposits would be far more practical than those in drier areas. Current orbital data suggests several candidate regions where tube-like pit structures and ice-bearing terrain overlap. Identifying the best sites for early settlement will be one of the practical tasks of robotic precursor missions in the years ahead. Water, in the end, is not a secondary concern for a Mars civilization. It is close to the center of everything, from radiation shielding to food production to the simple human pleasure of a warm drink at the end of a long day underground. The resources exist. The question now shifts from whether a lava tube settlement could sustain itself to how the people inside it would experience the passage of time, the management of their days, and the maintenance of their inner lives across months and years of underground living. Part 7. The psychology of permanent underground living. There is a long tradition of humans living and working underground for extended periods, and almost all of it has been involuntary or temporary. Miners, submariners, researchers at polar stations, and participants in isolation studies have each contributed something to our understanding of what enclosed, light-controlled, socially limited environments do to the human mind over time. The picture that emerges is nuanced. People are more adaptable than we sometimes assume. But adaptation has limits, and those limits are shaped by factors that habitat designers can either ignore or take seriously. Isolation and confinement are the two variables most consistently linked to psychological difficulty in enclosed environments. Isolation refers to the separation from the broader human world, the awareness that ordinary life is inaccessible. Confinement refers to the physical limitation of movement, the inability to simply walk outside and let the horizon expand. On Mars, both factors would be present in their most extreme form. The planet itself is the barrier. There is no outside walk, no view of open sky without a spacesuit and the planning that entails. What research from analog environments suggests is that the management of these pressures depends heavily on several controllable variables. Meaningful work is among the most important. People in isolated environments who have clear, engaging tasks to perform, work that connects to a larger purpose and produces visible results, report substantially better psychological outcomes than those whose roles feel routine or purposeless. A Mars settlement, by its nature, would be engaged in genuinely important work. Every system would need attention, every discovery would carry significance, and the awareness of being part of something historically unprecedented tends to sustain motivation in ways that more ordinary circumstances do not. Social structure matters enormously. Small groups in confined spaces develop hierarchies, tensions, and alliances with a speed and intensity that larger social environments dilute. The Mars 500 study, in which 6 participants spent 520 days in a sealed facility simulating a Mars mission, found significant variation in individual outcomes. Some participants maintained stable mood and performance throughout. Others showed progressive sleep disruption, reduced activity, and what researchers described as a kind of psychological withdrawal. The differences were linked partly to personality and partly to how the group managed conflict and communication. For a lava tube settlement growing beyond a small crew, the social dynamics would shift in ways that are broadly positive. More people means more social options, more skill diversity, and the development of informal community structures that provide support outside of formal mission roles. Children born in such a settlement, a generation raised underground on Mars, would have a relationship to that environment fundamentally different from the adults who arrived from Earth. For them it would simply be home, with all the psychological grounding that word implies. Privacy is a variable that confined environment research identifies as surprisingly powerful. People who have some space that is genuinely their own, where they can be alone and unobserved, report better well-being than those in communal arrangements without private retreat. In early Mars habitats, space would be limited and privacy a genuine engineering challenge. But even small sleeping pods with closing doors, their own lighting controls, and acoustic separation from shared spaces can satisfy the basic psychological need for a territory that belongs to the individual. Boredom and monotony are real risks in any enclosed, repetitive environment, and a lava tube settlement would have both. The view does not change. The weather does not change, because there is no weather inside. The same corridors, the same faces, the same sounds repeat day after sol. Research on long-duration spaceflight identifies what some scientists have called the third quarter phenomenon, a dip in mood and performance that tends to occur roughly 3/4 of the way through a mission, when the novelty has worn off and the end is still not close. Managing this in a permanent settlement, where there is no defined endpoint, would require deliberate programming of novelty, celebration, seasonal rhythms, and regular variation in routine. Sleep sits at the intersection of all these psychological concerns. Stress elevates cortisol, which disrupts sleep. Social conflict disrupts sleep. Monotony can paradoxically disrupt sleep by flattening the distinction between active and rest periods. A settlement where sleep is treated as a primary health metric, monitored and supported systematically, would be managing not just the physiology of rest but the psychological architecture of a functioning community. The underground environment, for all its constraints, offers one psychological gift that the surface cannot easily match: safety. The rock overhead, the sealed and stable atmosphere, the absence of storms and radiation, and the hostile Martian sky creates an environment that the body and mind can recognize, with the right design and support, as genuinely sheltered. That sense of shelter, of being contained within something protective, is not a minor thing. It is, at a very deep level, what a home is. The psychology of underground Mars living is not solved, but it is being taken seriously. And the insights being gathered now, from submarines, polar stations, isolation studies, and spaceflight, are the foundation on which livable underground communities will eventually be built. The human mind needs more than shelter to thrive, though. It needs beauty, meaning, and connection to something larger than the daily routine. How designers are beginning to think about that, in the specific context of permanent underground habitats, is where we turn next. Part 8. Designing for Well-Being in the Dark. There is a discipline called evidence-based design, which applies research findings from psychology, neuroscience, and environmental studies directly to the design of built spaces. It asks not only whether space is functional but whether it supports the well-being of the people who inhabit it. Hospitals that use it report faster patient recovery. Schools that use it show improved attention and reduced stress. The principles it has developed are increasingly being applied to the unusual problem of extreme environment habitats, including those proposed for the Moon and Mars. The core insight of evidence-based design, stated plainly, is that the physical environment shapes mental and physical health in measurable ways, and that this happens whether we design for it intentionally or not. A space that is poorly lit, acoustically harsh, visually monotonous, and without connection to nature will degrade the well-being of its inhabitants over time, even if every technical survival system is functioning perfectly. A space designed with human psychology in mind can actively support mood, cognitive function, sleep, and social cohesion, even in circumstances of extraordinary isolation. For a Martian lava tube habitat, the most basic design intervention is also the most powerful: Variety. The human perceptual system is calibrated for a world of changing light, shifting seasons, and environmental diversity. It registers sameness as a kind of low-level stress. In a sealed underground environment, creating variety requires intentional effort. Lighting systems that change color temperature and intensity across the day do some of this work. Spaces with different scales and characters. A high-ceilinged communal area near the raw rock wall versus a low-ceilinged, warmly lit dining space give the perceptual system different experiences to process. Color has measurable effects on mood and arousal. Cool blues and greens are associated with calm and focus. Warm yellows and oranges with comfort and social ease. Reds tend to increase arousal and may not be appropriate in rest areas. A habitat designed with color intentionality, using different palettes in different zones to support the activities that take place there, would be using the environment as a passive behavioral tool. Sleeping quarters would lean toward cool, neutral tones that do not stimulate. Social spaces might use warmer colors that encourage relaxed interaction. Work areas could be designed for the specific cognitive demands they serve. Biophilic design, the incorporation of natural elements into built environments, is consistently supported by research as a contributor to well-being. Contact with living plants, the sound of water, natural materials and textures, and views of organic rather than purely geometric forms all appear to reduce stress markers and improve reported mood. In a lava tube habitat, the raw rock of the tube walls, if incorporated into the design rather than hidden entirely behind paneling, would provide a powerful biophilic element. Stone has texture, variation, and color that no manufactured surface fully replicates. Leaving sections of the original basalt wall exposed, smoothed perhaps but not concealed, would give inhabitants a connection to the physical reality of their environment, a reminder that they are inside something ancient and real rather than inside a machine. Water features, even small ones, provide acoustic and visual benefits. A narrow channel of recirculating water, or a small fountain in a communal space, produces a sound that the brain processes very differently from mechanical noise. The sound of moving water is associated with relaxation in a remarkably consistent way across cultures. In an environment where every other sound is the product of engineering, the sound of water moving naturally, even through an artificial channel, provides something the nervous system recognizes as fundamentally unthreatening. Sleep-specific design in a lava tube habitat would take the principles of terrestrial sleep science and apply them without compromise. Complete darkness on demand. Thermal control at the individual level, since preferred sleep temperature varies between people. Acoustic isolation sufficient to reduce background noise to the low levels, below roughly 30 decibels, associated with uninterrupted sleep. Personal control over all of these variables, because research consistently shows that perceived control over one's sleep environment improves sleep quality even when the objective conditions are similar. Mattress and bedding design matters more in low-gravity simulation environments, and the partial gravity of Mars, 38% of Earth's, would change how the body rests against a surface. Some researchers have suggested that Martian gravity might actually reduce pressure point discomfort during sleep, since the force pressing the body against the mattress is substantially lower. Whether this translates to better sleep quality in practice is not yet known, but it is one of the many small ways in which the Martian environment might surprise us with an unexpected benefit. The overall goal of all this design work is something simple to state and difficult to achieve. A place where a person feels, at the end of each day, that they are somewhere rather than nowhere. Somewhere with character, with warmth, with beauty in its particular way. The underground does not have to feel like a bunker. With intention and knowledge, it can feel like home. As the habitat grows and the community inside it develops its own rhythms, traditions, and culture, design will be shaped increasingly by the people who live there rather than only by engineers on Earth. That evolution, from designed space to inhabited place, is one of the most important transitions any settlement can make. Part 9. Power, Energy, and the Heartbeat of an Underground World. Every system in a Martian lava tube habitat depends on energy. Light, heat, air circulation, water extraction, food production, communications, medical equipment, and the dozens of smaller systems that keep a sealed environment livable all draw from the same supply. Energy is not one concern among many for an underground Mars settlement. It is the underlying condition on which everything else rests. If power fails, the habitat does not become uncomfortable. It becomes dangerous, quickly. Understanding the energy challenge begins with appreciating the distance. Mars receives roughly 43% of the solar energy that Earth does, simply because of its greater distance from the Sun. On a clear day at the equator, solar panels on the Martian surface can generate useful electricity. But clear days are not guaranteed. Dust accumulates on panels continuously, reducing their output gradually and sometimes dramatically. Global dust storms, which can last for weeks or months, have reduced sunlight at the surface to a small fraction of its normal value. The Opportunity rover, which relied on solar power, fell silent during the global dust storm of 2018 when its panels could no longer generate sufficient charge. A human settlement cannot afford that vulnerability. For a lava tube habitat, surface solar arrays connected by cable to the underground living space are a viable component of an energy system, but not a sufficient one alone. The arrays would need to be large, regularly cleaned, and redundantly designed. Their output would feed battery storage systems capable of bridging gaps during storms and overnight periods. This is manageable engineering, but it introduces dependencies on surface conditions that an underground habitat is otherwise designed to escape. Nuclear fission power is the alternative that most mission planners consider essential for a serious, long-duration Mars presence. A compact fission reactor, operating on enriched uranium fuel brought from Earth, can generate continuous, reliable power independent of sunlight, dust, or season. NASA and the Department of Energy have been developing the kilopower reactor concept, a small fission system designed specifically for planetary surface applications, with ground tests demonstrating promising results. A scaled version of such technology could provide the baseline power a small settlement requires, with additional units added as the community grows. The combination of nuclear baseline power and supplemental solar, with battery storage bridging gaps, represents the energy architecture most discussed for early Mars habitats. Redundancy is the governing principle. No single failure should be able to cut power entirely. Systems back up systems, and the margins are calculated conservatively. Heat management in an underground habitat has an interesting dual character. The habitat must be warmed, because the surrounding rock is cold and the Martian environment would drain heat from a pressurized space continuously without active heating. But equipment, computers, and human metabolism all generate heat, and in a sealed environment that heat accumulates. Thermal management systems must both add heat to living spaces and remove it from equipment spaces, distributing it carefully to maintain comfortable temperatures throughout. The cold rock of the tube walls is actually useful here as a passive heat sink for electronics, drawing waste heat away from sensitive systems without additional energy cost. Energy storage technology will be critical as the settlement grows. Batteries capable of storing large amounts of energy efficiently and cycling through charge and discharge thousands of times without significant degradation are an active area of development. Hydrogen fuel cells, which store energy chemically and release it as electricity and water, are another option with the advantage that the water byproduct is directly useful. A settlement with surplus solar power during calm periods could use electrolysis to split water into hydrogen and oxygen, store the hydrogen, and recombine it in fuel cells during high demand or low generation periods. The water cycle and the energy cycle become linked in a system of elegant, if complex, interdependence. As the settlement scales, energy demand grows, but so does the sophistication of energy management. Larger communities can implement smarter distribution, running energy-intensive processes like water extraction and manufacturing during periods of surplus and deferring them when supply is tighter. The underground environment, stable and predictable in ways the surface is not, actually simplifies some aspects of thermal and energy management by removing the daily surface temperature cycle from the equation. Energy, in a functioning settlement, becomes something close to invisible, the way plumbing and electricity are invisible in a well-maintained building on Earth. It is only noticed when it fails. The engineering goal is to make failure so unlikely and so well managed that it never interrupts the quiet, steady rhythm of daily life underground. And that rhythm, the dependable heartbeat of a powered, heated, lit, and breathing habitat, is what allows everything else to happen. Work, community, rest, and sleep all depend on it. The power flowing through the cables buried in the basalt floor is, in its own prosaic way, the pulse of the civilization growing inside the rock. The energy question connects directly to another that shapes every aspect of underground life: how the settlement communicates with Earth, manages time across interplanetary distances, and maintains the human connections that sustain people through long periods of isolation. Part 10: Communication, Time, and the Distance Between Worlds. Mars and Earth are separated by a distance that varies considerably as both planets travel their orbits around the Sun. At their closest approach, called opposition, the gap can shrink to around 54 million kilometers. At their farthest, on opposite sides of the Sun, the distance stretches to over 400 million kilometers. Light, and therefore any radio signal, travels at a fixed speed of roughly 300,000 kilometers per second. Even at closest approach, a message from Mars takes about 3 minutes to reach Earth. At maximum separation, the delay extends to over 20 minutes each way. A conversation in the ordinary sense, with a reply following a statement after a brief pause, is impossible across interplanetary distances. Every exchange is a letter, sent and awaited. For a lava tube settlement, this communication reality shapes daily life in ways both practical and psychological. Mission-critical decisions cannot be referred to Earth and answered in real time. Engineers on Mars must solve problems themselves, in the moment, drawing on their own expertise and judgment. Medical emergencies cannot wait for a consultation that might take 40 minutes round trip under favorable conditions. The settlement must be functionally self-sufficient in its decision-making from very early in its existence, not as a goal for some distant future but as an operational necessity from the first day. This is a profound shift from how human space exploration has worked historically. Apollo astronauts on the Moon could speak with mission control in Houston with a delay of only a little over a second. The crews of the International Space Station communicate with ground teams in near real time. The psychological safety net of immediate expert support has always been present. On Mars, that net is absent. The crew is on their own, advised and supported but not directed in the moment. Research on isolated and confined environments suggests that this autonomy can be positive as well as challenging. Crews that develop strong internal decision-making processes and trust their own competence tend to perform well over long missions. The shift from being directed to being self-directing is associated, in the better outcomes, with increased cohesion and a stronger sense of shared purpose. The settlement is not a branch office. It is its own entity, solving its own problems, making its own choices. Timekeeping on Mars would develop its own character. The Martian sol of 24 hours and 37 minutes would become the natural unit of daily life. Mars has its own calendar, a year of roughly 687 Earth days divided into seasons by its elliptical orbit and axial tilt. A settlement that has been on Mars for several years would begin to develop a relationship to Martian seasons, even underground where those seasons have no direct environmental effect. Tracking the Martian year, naming its seasons and marking their passage, would be part of the cultural architecture of the community, a way of being located in time on a world that is genuinely its own. Communication with Earth, despite its delays, would remain a vital lifeline. Regular scheduled transmissions carrying scientific data, personal messages, news from home, entertainment, and updated technical guidance would structure the communication calendar. Personal messages from family and friends on Earth, arriving with their embedded delay and replied to with the same, would be one of the most psychologically significant resources available to settlers. The asynchronous letter, thought to have been superseded by instant communication, would reassert itself as the medium of connection across space. Sleep and rest would intersect with communication schedules in a specific way. If Earth-facing transmissions are scheduled at particular times in the Martian sol, those times would become anchor points in daily routine. The discipline of maintaining regular sleep schedules would align with the broader need for predictable structure in an isolated environment. A community that collectively keeps consistent sleep-wake timing also collectively maintains the alertness and decision-making capacity that self-reliance demands. The distance between Mars and Earth is not only physical. It is also the distance between a known world and an unknown one, between the accumulated support of human civilization and the small, self-contained community making its way in the underground dark. That distance is part of what makes a Mars settlement genuinely new in human history. It is also, for some of the people who will choose to make that journey, part of the appeal. Connection and isolation, delay and self-reliance, the rhythm of Martian time and the echo of Earth time in personal messages and remembered seasons. All of these flow together in the daily experience of underground life. The next question is what that daily experience might actually look and feel like, lived out across the hours of a Martian soul. Part 11. A day in the life below the surface. It begins, as all days begin, with light, not sunlight. There is no sunlight here, 4 meters below the basalt surface of the Tharsis Plateau, inside the pressurized sleeve of humanity's first permanent lava tube settlement. What comes instead is a slow, engineered brightening on the ceiling panel above the sleeping pod, beginning with a faint warm amber that deepens almost imperceptibly through the first minutes, then gradually shifting cooler and brighter as the simulated dawn builds. The process takes 30 minutes from first light to full morning brightness, and by the time the panel reaches its peak intensity, the person inside the pod is already stirring, pulled upward from sleep by biology rather than alarm. This is not a fanciful detail. The biology of gradual light exposure is well understood. Melatonin suppression begins before the eyes fully open. Cortisol, the hormone of morning alertness, begins its daily rise in anticipation of the light. The body wakes from the inside out, prepared rather than startled, and the day begins with a physical readiness that poor sleep environments regularly undermine. The pod itself is small by some standards. Roughly 2 meters long, 1.5 meters wide, with enough height to sit up comfortably. The walls and ceiling can display any image or pattern the occupant has chosen, and many people settle on something organic, a forest canopy, a slow river, a cloudy sky, not for simulation but for the simple comfort of seeing something that did not come from a machine. A small vent near the head of the bed delivers air at the precise temperature and humidity the occupant has set. The mattress has distributed its pressure evenly across the night. The acoustics of the pod, lined with sound-absorbing panels, have kept the background hum of the habitat from penetrating. Outside the pod, the main corridor of the habitat extends in both directions into the lit distance. The rock of the original tube wall is visible in places, a dark, rough basalt surface that catches the light differently from the manufactured panels beside it. Several people are already in the communal kitchen, preparing food from stores and from the most recent harvest of the hydroponic bays. The smell of coffee, grown in a small dedicated section of the plant wall, moves through the air. It is perhaps the most ordinary thing in an entirely extraordinary place. The workday on a Mars settlement would be structured and purposeful. Maintenance of habitat systems, scientific research, geological surveys conducted via remotely operated surface vehicles, agricultural management, medical monitoring, construction planning for the next phase of expansion. There is no shortage of meaningful tasks. Work in extreme environment psychology is consistent on this point. The feeling of contributing to something necessary and significant is among the strongest available protections against the psychological erosion that isolation can otherwise bring. Meals are communal by design as much as by necessity. Research from isolated environment studies identifies shared mealtimes as one of the most important social rituals available, a daily structure around which informal communication, relationship maintenance, and the simple pleasure of eating together can anchor the rhythms of community life. In the lava tube habitat, the communal dining area is one of the largest and most carefully designed social spaces, with warm lighting, a high ceiling that incorporates a section of the raw tube roof, and seating arranged to encourage conversation rather than parallel solitude. Physical exercise occupies a significant portion of each day, not as leisure but as medical necessity. Mars's gravity at 38% of Earth's means that the body is under less mechanical load than it evolved to expect. Without deliberate, sustained exercise, bone density decreases and muscle mass declines at rates that would eventually compromise health and function. Resistance exercise equipment designed for small spaces allows inhabitants to load their skeletons and muscles against artificial resistance. Treadmills and cycling equipment provide cardiovascular work. Exercise schedules are not optional and are tracked as health data. The hours between the end of the structured workday and sleep are perhaps the most revealing of what daily life in the underground would feel like. Some people read. Some make music, and the acoustic quality of the larger common spaces lends itself to this in a way that the original designers considered carefully. Some work on personal projects, studies, writing, craft, the kind of activity that serves the self rather than the mission. Some simply talk, gathered in the warm light of the social space with the slow hum of the habitat around them. As the soul winds toward its end, the lighting system begins its evening sequence. Color temperature shifts from the cool, alert white of working hours toward a warm amber. Intensity drops gradually. The body reads these signals without being asked, and melatonin begins its rise. The habitat, which has been generating tasks and engagement all day, begins to quiet. Voices lower. Movement slows. The pod receives its occupant in darkness that is complete, in silence that is close to total, and in a temperature that has been set to the narrow range in which that particular person sleeps best. The ceiling panel is dark. The vent is quiet. Somewhere beyond the rock, on a surface no one inside can see, the Martian night is cold and brilliant with stars. But here, below, there is only warmth and stillness. Sleep comes, as it is designed to come. Deliberately, gently, and on time. Part 12. The Science of Sleep at 38% Gravity. Sleep on Earth is shaped by gravity in ways so fundamental that we rarely think about them. The body lies down because lying down removes the mechanical load of supporting itself against a one-gravity field. Blood redistributes. The spine decompresses. The cardiovascular system shifts into a lower effort mode. The whole physical architecture of sleep, from the horizontal posture to the softness of a mattress compensating for pressure points, evolved in the context of Earth's gravitational pull. Mars offers 38% of that pull, and what this means for sleep is genuinely uncertain, because no human has yet slept there. What we have are inferences from analogs and from spaceflight data. Astronauts aboard the International Space Station sleep in microgravity, which is a more extreme departure from Earth conditions than Martian gravity would be. In microgravity, the absence of gravitational loading changes fluid distribution in the body significantly. Fluids shift toward the head and upper body, causing facial puffiness, nasal congestion, and a sensation that some astronauts describe as a persistent mild headache. Sleep quality in microgravity is notably poor for many crew members, and while multiple factors contribute, the fluid redistribution and the absence of the body's familiar positional cues for sleep are considered relevant. Martian gravity, at 38% of Earth's, is substantially more than zero. The body would still experience a clear up and down orientation. Fluids would not migrate toward the head as dramatically as in microgravity. A person lying on a mattress on Mars would feel the surface beneath them, would experience genuine pressure relief when lying down after standing and working. In this fundamental sense, sleep on Mars would resemble sleep on Earth more than sleep in orbit does. But the differences would be real. Pressure points, the areas where the body presses against a sleeping surface, would receive less force on Mars than on Earth. A mattress engineered for Earth's gravity would be firmer than necessary, potentially creating discomfort in a different way by not conforming appropriately to a body that is pressing against it with less force. Bedding, pillow support, and mattress design would all need to be rethought for the Martian gravitational context. This is not an insurmountable problem, but it is a specific one that sleep engineers would need to address deliberately rather than assuming that equipment designed for Earth would transfer without modification. Breathing during sleep may also be affected. On Earth, certain sleep-disordered breathing conditions are worsened by the way gravity affects airway anatomy in specific sleeping positions. Whether reduced gravity would improve, worsen, or simply alter these patterns is not fully understood. The diaphragm, which does much of the work of breathing, would experience less gravitational resistance in the lower gravity environment. Some researchers have speculated that breathing during sleep might actually be somewhat easier on Mars than on Earth for this reason, though this remains theoretical. The circadian system itself does not directly depend on gravity, but the physical sensations that normally reinforce sleep and waking have gravitational components. The heaviness of the body at rest, the physical relief of lying down, the effort of rising, all contribute to the felt experience of the sleep-wake cycle. On Mars, these sensations would be subtly different, lighter, and less emphatic. Whether this would make the transition into sleep easier or harder, whether the body would find it more or less difficult to recognize that it is in a rest state, is a question that only experience on Mars will answer with certainty. Bone and muscle physiology during sleep is also relevant. Sleep is not a passive state for the body's structural tissues. Growth hormone is released during deep sleep and plays a role in bone and muscle maintenance. In an environment where bone density loss from reduced gravitational loading is an ongoing concern, the quality and depth of sleep becomes medically significant beyond its effects on cognitive performance and mood. Poor sleep that reduces growth hormone release would compound the skeletal challenges of low-gravity living. Good sleep, supported by the carefully engineered environment of the lava tube habitat, would work in the opposite direction, supporting the body's maintenance processes during the hours of rest. There is one more consideration that is easy to overlook. The psychological sense of safety during sleep has physiological correlates. A body that is in a perceived safe environment, one that is familiar, sheltered, and free from perceived threat, enters deeper and more restorative sleep stages more readily than one that is in an unfamiliar or threatening context. The first nights in a new environment are typically the worst for sleep quality, a phenomenon sometimes called the first night effect, and it takes time for the brain to reclassify a new space as safe. For settlers arriving on Mars and descending into their underground habitat for the first time, this adjustment period would be real and should be managed with patience and expectation setting rather than concern. Over time, the habitat becomes known. The sounds become familiar. The darkness becomes expected and welcome. The body learns that this is where it sleeps, and sleep improves. The science of sleep at 38% gravity is still being written, but the principles that will govern it are the same principles that govern sleep anywhere: safety, darkness, temperature, and time. What keeps those conditions stable? and what happens when they are threatened, brings us to the systems designed to protect the habitat from the unexpected. Part 13: Redundancy, Resilience, and the Art of Not Dying. There is a principle in life-critical engineering that is stated simply but demands enormous complexity in practice. Never have a single point of failure. Any system whose malfunction would be immediately catastrophic must have a backup. Any backup that is itself critical must have a backup of its own. The layers of redundancy in a spacecraft or a sealed habitat are not the product of excessive caution. They are the minimum requirement for operating in an environment where the outside offers no help and no second chances. A Martian lava tube habitat would be among the most demanding applications of this principle ever attempted. The environment surrounding it is lethal. The distance from Earth makes resupply and rescue impossible on any timescale relevant to an acute emergency. Every system that the habitat depends on for survival, atmosphere, pressure containment, heating, power, water, and food production, must be designed with failure modes that are graceful rather than catastrophic, and with backup systems capable of sustaining life while repairs are made. Atmosphere management is the most immediately critical system. The pressurized liner holding breathable air against the Martian near vacuum must maintain its integrity continuously. A small leak, properly detected and managed, is a maintenance problem. A sudden, large breach is a different matter entirely. Habitat design addresses this through compartmentalization, dividing the interior into sections that can be sealed independently, so that a breach in one area does not depressurize the whole. Pressure sensors distributed throughout the habitat provide continuous monitoring, with automated alerts and responses triggered by any deviation from nominal. The air supply itself requires management beyond simple pressure maintenance. Carbon dioxide exhaled by inhabitants must be removed continuously. Oxygen must be replenished. The carbon dioxide removal systems used on the International Space Station, which use chemical absorbers and regenerative processes, are well understood and would be adapted for Mars. Oxygen can be generated through electrolysis of water, a process that splits water molecules into hydrogen and oxygen using electrical current. The oxygen is retained for breathing, and the hydrogen can be used as fuel or vented safely. Having multiple independent systems for both carbon dioxide removal and oxygen generation, each capable of sustaining the habitat alone, is standard in life support design. Heating failure in a Martian underground habitat would be dangerous but not instantly fatal in the way that pressure loss would be. The thermal mass of the surrounding rock would slow the rate of temperature decline, giving inhabitants time to diagnose and address the problem, or to don thermal protection while repairs proceed. Nevertheless, heating redundancy is designed carefully, with backup heating elements, insulated emergency shelters within the habitat for worst-case scenarios, and warm suits available at all times. Food and water redundancy is managed through storage as much as through system redundancy. Maintaining a reserve supply sufficient for a defined number of sols, independent of active production, gives the settlement a buffer against disruption of growing or extraction systems. Early in a settlement's life, this buffer would be partially supplied from Earth. As local production matures, the buffer can be maintained from local reserves. Medical emergencies are a specific category of risk that redundancy thinking applies to differently. You cannot build a backup for a trained surgeon in the way you can build a backup power supply. What you can do is ensure that multiple crew members have substantial medical training, that diagnostic and surgical equipment is available and maintained, and that telemedicine consultation with Earth specialists is factored into medical planning despite the communication delay. Robotic surgical assistance, guided remotely by Earth-based specialists with the delay managed through pre-planned protocols, is an area of active research for exactly this application. Sleep, in a resilience context, is itself a risk management tool. A crew that is consistently well-rested makes better decisions, catches errors earlier, responds to emergencies more effectively, and maintains the interpersonal cohesion that collective problem-solving depends on. Sleep deprivation degrades all of these capacities in ways that accumulate invisibly until a moment of acute demand reveals them. An accident or system failure is precisely the moment when cognitive performance and team function matter most. The investment in sleep quality is therefore also an investment in the settlement's ability to survive the unexpected. The philosophy of resilience in an underground Mars habitat is not about eliminating risk. That is impossible. It is about ensuring that risks are known, planned for, and managed through systems and practices that keep single failures from cascading into catastrophe. Every backup system, every stored reserve, every trained skill represents a layer of distance between a problem and a disaster. The rock overhead is itself the largest single element of resilience. It does not require maintenance. It does not consume power. It does not have software that needs updating. It simply sits there, billions of years old, shielding everything beneath it from radiation and the surface environment with the patient, unconditional reliability of geology. Resilience is what allows a settlement to persist long enough to grow, and growth brings its own questions, not just of engineering and logistics, but of identity, culture, and what it means to be human in a place no human evolved to inhabit. Part 14. The first Martian generation. Every civilization that has ever existed on Earth began somewhere. A valley, a riverbank, a coastline where conditions were favorable enough to sustain a community through its fragile early years. Those first communities carried the cultural inheritance of wherever their founders came from, and then, over generations, they developed something new. Languages shifted. Practices adapted. New traditions formed around the specific conditions of the new place. The civilization that eventually emerged was shaped as much by where it grew as by where it came from. The first generation of children born on Mars would be something genuinely new in human history. Not visitors, not pioneers making a temporary sacrifice, but people for whom the lava tube habitat is simply the world. They would have no direct memory of Earth, no personal experience of open sky or rain or the smell of a forest. Their entire physical and social reality would be the sealed, lit, carefully managed interior of an underground settlement on another planet. This prospect raises questions that scientists, ethicists, and philosophers are beginning to take seriously. The most immediate is physiological. A child developing in 38% gravity would experience different mechanical loading on their skeleton and muscles than a child developing on Earth. Bone growth is responsive to mechanical load, and bones that are not loaded appropriately during development may not achieve the density and structure that Earth gravity normally induces. Whether children born and raised in Martian gravity would develop normally by Martian standards, adapted to the environment they will actually live in, or whether they would face health challenges from the gravitational difference, is a question that cannot currently be answered with confidence. What is known from terrestrial developmental science is that children are remarkably adaptive. The developing brain and body calibrate themselves to the environment they encounter, building physical and cognitive structures suited to the demands of that environment. A child raised in Martian gravity might develop a body that is optimized for Martian gravity, with proportionally different bone structure and muscle distribution than an Earth-born adult. Whether that body would be healthy in its own context, whether it could sustain the physical demands of Martian life, is the critical question. Cognitively, children on Mars would grow up in a rich and demanding environment. The settlement would be a place of constant learning, problem-solving, and purposeful work. Educational structures would develop organically from the needs and capacities of the community, drawing on Earth-based curricula transmitted digitally but adapted to the specific realities of Martian life. A child who grows up understanding life support systems, hydroponics, geology, and the engineering of sealed environments from direct daily experience would have a practical knowledge base of extraordinary depth. Psychologically, the question of identity for the first Martian generation is perhaps the most fascinating. Earth would be a distant point of light in their sky, the origin of their parents and grandparents, the source of transmissions and stories and cultural inheritance, but not their home. Mars would be their home, in the deepest and most literal sense. The lava tube, the recycled air, the engineered light, the rhythm of the Martian soul, the community of people who share their world. This would be the entirety of their experienced reality. Their relationship to sleep and the rhythms of day would be entirely shaped by the artificial environment of the habitat. They would never have experienced a natural sunrise or a thunderstorm or the sound of wind in trees. Their circadian rhythms would be entrained from birth to the engineered light cycles of the settlement. In a strange way, they would be the most perfectly adapted sleepers in human history for their specific environment. Their biology calibrated from the very beginning to the light and dark cycles that the habitat provides. The cultural life of a first Martian generation would be built from what their parents brought and what the environment demanded. Art made with available materials. Music shaped by the acoustic properties of the spaces where it is played. Stories that reference a landscape no member of the community has ever stood in openly, but that all of them know as the world just beyond the rock. Language that develops its own vocabulary for Martian realities, for the specific quality of recycled air, for the sound the habitat makes in the deep part of the night, for the particular darkness of a sealed sleeping pod at rest. This is how civilizations form. Not through grand declarations but through the accumulation of small, specific adaptations to a particular place. The children of Mars would be the first humans for whom Mars is not a destination or a challenge but simply where they are from. That simple fact would shape everything about who they become. Their sleep would be their own. Their days would be their own. The ancient rock around them would be theirs in a way it can never quite be for the people who arrived from somewhere else. And in that belonging, however strange and hard one, something genuinely new in the human story would be taking root. Part 15. Terraforming Dreams and the Limits of the Possible. There is a long-standing debate in the science and philosophy of Mars exploration that cuts to the heart of what a human presence on that planet is ultimately for. On one side is the idea of terraforming, the deliberate, large-scale modification of Mars to make its surface more hospitable to Earth life, ideally over centuries or millennia, transforming it into a world where humans might eventually walk outside without pressure suits. On the other side is the position that Mars should be left as it is, or at minimum that any modification should be minimal, both out of respect for the planet's own scientific value and out of caution about the unintended consequences of planetary-scale engineering. The lava tube habitat strategy sits in an interesting position relative to this debate. It does not require terraforming. It does not wait for it. It proposes instead that humans can build a sustainable, expanding civilization on Mars right now, using the planet's existing architecture, without needing to change the planet at the surface level to do so. In that sense, underground habitation is the practical alternative to terraforming, not its precursor. But the terraforming dream does not disappear simply because underground habitation is viable. It persists because of what it represents: the possibility of an open sky, of rain, of standing on the surface of Mars in ordinary clothing and feeling the wind on your face. These are not trivial desires. They speak to something deep in the human relationship with the natural world, a relationship that underground habitation, however well designed, cannot fully replicate. The scientific obstacles to terraforming Mars are formidable and in some respects may be insurmountable with foreseeable technology. The most fundamental problem is atmospheric pressure. Mars's atmosphere is too thin to support liquid water at the surface or to provide meaningful radiation shielding. Thickening it to Earth-like pressure would require introducing enormous quantities of greenhouse gases, primarily carbon dioxide, to warm the planet and drive a cascade of changes that might eventually produce a denser atmosphere. Proposals have included vaporizing the polar carbon dioxide ice caps with orbital mirrors or releasing greenhouse gases from subsurface deposits. Even the most optimistic assessments suggest this process would take centuries at minimum. And the endpoint is uncertain because Mars lacks the magnetic field needed to prevent the solar wind from stripping away a thickened atmosphere over geological time. Without a magnetic field, any terraformed Martian atmosphere would be slowly eroded by the solar wind, the stream of charged particles flowing outward from the Sun. On Earth, the magnetosphere deflects this wind continuously, protecting the atmosphere from loss. Mars lost its global magnetic field billions of years ago, and regenerating it would require restarting the planet's core dynamo, a prospect so technically remote that most serious discussions of terraforming simply set it aside and work around it. Some proposals suggest placing a magnetic shield at the Mars-Sun Lagrange point, an artificial structure that would deflect the solar wind before it reaches Mars, reducing atmospheric loss rates sufficiently to make terraforming viable over long timescales. This idea is taken seriously by some researchers, but it remains entirely theoretical. The ethical dimension of terraforming becomes more complex if Mars harbors life, even microbial life, in subsurface environments where liquid water might exist. The lava tube habitat, from this perspective, raises its own ethical questions. Human activity inside a tube, even a sealed and careful one, introduces Earth organisms into a Martian environment. Contamination protocols for planetary protection are strict for robotic missions, but a crude settlement would inevitably bring a complex ecosystem of human microbiomes, bacteria, fungi, and viruses into contact with the Martian environment. If Mars does harbor indigenous life, the implications of that contact are profound and largely unknown. The underground strategy, however, carries a lighter planetary footprint than surface-based habitation would. A sealed habitat inside a lava tube concentrates human activity in a defined, contained space. It does not spread across the surface. It does not require the large-scale atmospheric interventions that terraforming demands. If Mars does harbor life in subsurface environments, the question of how human underground habitats interact with those environments would need careful scientific investigation before and during settlement. But the contained nature of lava tube habitation makes that investigation more tractable than a diffuse surface presence would be. The dreams of terraforming and the reality of lava tube habitation are not mutually exclusive over very long timescales. A civilization that begins underground, grows in population and capability across generations, and eventually develops the technology and resources to address the surface environment is following a path that has historical echoes. Underground habitation as a foundation, surface exploration as an expanding frontier, and the very distant possibility of an open sky as a generational aspiration. This sequence is coherent, even if the final step remains far beyond current capability. For now, and for the foreseeable future, the rock overhead is not a limitation to be overcome. It is the condition that makes everything else possible. The dreams of open sky are real and worth holding. But the life being built beneath the surface is real too. And it does not need to wait for the sky to open in order to be worth living. The civilization taking root in the underground does not exist in isolation from the broader human story. It is connected to Earth through communication, culture, and shared history, and the relationship between those two worlds will shape both of them in ways that are only beginning to be imagined. Part 16. Earth and Mars, a relationship across space. The relationship between a Mars settlement and Earth would be unlike any relationship between a colony and its origin world in human history. Distance is the defining factor. The British colonies in North America were weeks away by sailing ship. The settlement patterns of human prehistory, the spread of populations across continents, took place over generations on a continuous landmass. Even the most remote human communities on Earth share the same atmosphere, the same sky, and the same biological web of life. Mars would be separated from Earth not by ocean or mountain range, but by an interplanetary gulf that no human body can cross in less than several months under any foreseeable technology, and that no signal can cross in less than several minutes at best. This distance shapes the relationship in both directions. Earth would be the origin of the settlement's founders, the source of its initial technology, and the cultural inheritance embedded in every practice and tradition the settlers bring with them. The supply chains connecting Earth to Mars, at least in the early decades, would be literally life-saving. Replacement components, medical supplies, specialized equipment, and scientific instruments that cannot yet be manufactured on Mars would arrive on periodic cargo missions, planned years in advance around the orbital alignment windows that open roughly every 26 months when Earth and Mars are favorably positioned. Those launch windows are a structural feature of the relationship. Unlike a supply chain on Earth where a resupply can be dispatched on short notice, the orbital mechanics of Mars mean that there are defined periods when launches are efficient and long gaps between them. A settlement that runs out of a critical resource between windows faces a serious problem. This reality enforces a planning discipline and a culture of self-sufficiency that would become central to Martian identity. You plan for the gap. You maintain your reserves. You develop local solutions for as many needs as possible. Over time, as manufacturing capability on Mars grows, the dependency on Earth's supply chains would decrease. A settlement that can fabricate its own components from Martian materials, that can grow most of its own food, generate its own power, and extract its own water, would relate to Earth increasingly as a cultural and scientific partner rather than a supplier. This transition, from dependent outpost to self-sufficient community, would mark one of the significant thresholds in the development of a Martian civilization. The cultural relationship would be complex from the beginning and would grow more so over generations. The first settlers would carry Earth culture deeply within them, in their languages, their arts, their social norms, and their unconscious assumptions about how the world works. Their children, raised in the lava tube environment, would inherit that culture but filter it through a radically different lived experience. Over generations, the cultural distance between Mars and Earth might grow as significant as the physical one, producing a Martian culture that is recognizably rooted in Earth but distinctly its own. Communication, despite its delays, would sustain the relationship across that cultural evolution. The flow of information between the two worlds would be continuous and substantial. Scientific findings from Mars, of enormous value to Earth-based researchers, would travel outward on every transmission. News, art, music, literature, educational content, and personal communications would travel in both directions. The people of Mars would know Earth culture intimately, even without ever having been there, in the same way that someone deeply read in the history and literature of a country they have never visited can feel a genuine connection to it. The economic relationship between Earth and Mars would develop in ways that are difficult to predict but are worth considering. Mars may prove to be a source of scientific knowledge of enormous value, from its geology, its preserved ancient atmosphere, and potentially its biology. It may develop technologies adapted to its specific conditions that have broader applications. Over very long timescales, the resources of Mars, its minerals, its position in the solar system, its potential as a base for further exploration, could make it economically significant in ways that are today purely speculative. What is less speculative is the symbolic and psychological importance of a successful Mars settlement to the people of Earth. The knowledge that humanity has established a self-sustaining community on another planet, that we have extended the range of where human life is possible, carries a meaning that transcends economics. It changes the answer to the question of what human civilization is, and what it is capable of. That change in self-understanding may be among the most significant contributions a Mars settlement makes, not to Mars, but to Earth. The two worlds, connected by light-speed signals and periodic cargo flights, by shared cultural inheritance and diverging lived experience, would grow together and apart simultaneously, each shaping the other's understanding of what it means to be human. That ongoing relationship, patient and imperfect and genuinely new, is itself one of the great adventures of the story being told beneath the Martian rock. As the settlement matures and its relationship with Earth evolves, the question of governance, law, and social organization within the lava tube community becomes increasingly important. How people organize themselves in a sealed, isolated environment with no external authority to appeal to is a question with deep practical consequences. Part 17. Governance, Law, and Social Order Underground. Every community needs rules. The rules do not need to be written down, and they do not need to be enforced by an institution with formal authority, but they need to exist and be broadly accepted. Rules about how shared resources are used, how conflicts are resolved, how decisions that affect everyone are made, and what behavior is considered unacceptable. Without these agreements, explicit or implicit, a community cannot maintain the cooperation that its survival depends on. This is true on Earth, and it is true in a sealed habitat on Mars, where the consequences of social breakdown are not merely unpleasant but potentially fatal. The study of governance in extreme and isolated environments offers some instructive precedents. Antarctic research stations operate under a mixture of national law, institutional policy, and the informal social norms that develop within any small, long-term group. Submarines run under strict military hierarchy with clear chains of command. The International Space Station is governed by a complex set of interagency agreements that carefully allocate authority and responsibility among the participating nations and space agencies. Each of these models reflects the specific needs and origins of its environment, and none of them translates directly to a permanent civilian settlement on Mars. A lava tube settlement in its early phases would likely operate under the authority of whatever agency or consortium sponsored and funded it. Decisions would be referred to Earth when time permits and made on site when they cannot wait. This works for a small, mission-oriented crew with a shared understanding of purpose and a clear organizational structure. It becomes more complicated as the settlement grows, as the population diversifies, and as individuals with different backgrounds, values, and priorities begin to constitute a genuine community rather than a specialized team. The communication delay between Mars and Earth has direct governance implications. An Earth-based authority cannot respond to a Martian situation in real time. Instructions issued from Earth might arrive to find that circumstances have changed, that the situation they addressed has already resolved itself or become dramatically worse. Over time, a Mars settlement would need to develop genuine local authority, the capacity to make binding decisions about its own affairs without waiting for guidance from a planet that is tens of millions of kilometers away. What form that local authority takes is an open question, and one that thoughtful people disagree about. A settlement whose founders are scientists and engineers might naturally organize around expertise, deferring to whoever has the deepest relevant knowledge for a given decision. A more formally democratic structure, with elected representatives and defined processes for collective decision-making, would be more appropriate for a larger and more diverse community. Elements of both would probably coexist, with technical decisions delegated to experts and broader community decisions made through some form of collective process. Resource allocation would be among the most sensitive governance challenges. In an environment where water, air, energy, and food are all produced and managed by systems that require maintenance and have finite capacity, access to these resources cannot be left entirely to individual discretion. Yet overly rigid control of personal consumption would conflict with the sense of autonomy and dignity that sustained well-being requires. Finding the balance between collective resource management and individual freedom would be an ongoing negotiation rather than a solved problem. Conflict resolution in a small, sealed community has a character that larger social environments dilute. When you cannot leave, when the person you are in conflict with will be at the next meal and the one after that, the resolution of interpersonal conflict becomes a community health issue rather than a private matter. Mediation structures, clear processes for raising and addressing grievances, and cultural norms that value direct communication over suppressed resentment would all need to be developed and maintained actively. Analog environment research consistently finds that unresolved interpersonal conflict is among the most corrosive forces in small isolated groups, spreading beyond the parties directly involved and degrading the cohesion of the whole community. Sleep intersects with governance in a way that might not be immediately obvious. A community that is collectively sleep-deprived is a community with impaired judgment, reduced patience, and diminished capacity for the kind of careful, cooperative decision-making that good governance requires. Protecting sleep as a community norm, treating rest as a collective value rather than an individual preference, is in part a governance decision. A settlement that schedules noisy maintenance work during rest periods, or that allows work demands to consistently encroach on sleep time, is making a governance choice with real consequences for community function and safety. The governance structures that develop on Mars will be shaped by necessity, by the specific personalities and values of the founding community, and by the slow accumulation of precedent that eventually hardens into custom and then into something resembling law. They will be imperfect, as all human governance is. But in an environment where cooperation is not merely virtuous but essential for survival, the incentive to make governance work is stronger than in almost any other context imaginable. The social order of an underground Mars civilization will be built, like everything else in that environment, with intention and care, out of materials both ancient and new. Part 18. The Mineral Mind. Geology as a Living Partner. The rock of Mars is not merely a backdrop to the human story being written inside it. It is an active participant, a material with properties, history, and ongoing relevance to every aspect of life in the lava tube settlement. Understanding that rock, learning its composition, its structure, its thermal behavior, and its history, is not only a scientific pursuit. It is a practical necessity for anyone who intends to live inside it for years or decades. Martian basalt, the primary material of lava tube walls, is broadly similar in composition to oceanic basalt on Earth. It is rich in iron and magnesium silicates, with varying amounts of calcium, aluminum, and other elements depending on the specific volcanic history of the region. This composition makes it dense and mechanically strong, well suited to the structural role it plays as the ceiling and walls of a pressurized habitat. It also makes it potentially useful as a raw material. Basalt can be melted and cast into structural elements, drawn into fibers for insulation and reinforcement, and processed into glass-like materials with useful optical and thermal properties. A settlement with sufficient energy could manufacture building materials directly from the rock surrounding it, reducing dependence on supplies from Earth. The thermal properties of basalt are central to the comfort and energy efficiency of the habitat. Basalt has a relatively high specific heat capacity, meaning it can absorb a significant amount of thermal energy before its temperature rises noticeably. The large mass of rock surrounding the habitat acts as a thermal buffer, absorbing excess heat during periods of high activity and releasing it slowly when heating demand is higher. This passive thermal mass reduces the work that active heating and cooling systems must do, smoothing out the peaks and troughs of thermal demand across the Sol. In energy terms, the rock is doing work continuously, quietly, and for free. The geological history preserved in the tube walls is also a scientific resource of the first order. Lava tubes form in distinct layers as successive flows cool and solidify. Each layer represents a volcanic event, a moment in the geological history of Mars frozen in the stratigraphy of the rock. A settlement inside a lava tube would have direct access to this record simply by studying the walls around it. The chemical composition of different layers can reveal information about the evolution of Martian volcanism over time. Isotopic analysis can provide age estimates. Trace element patterns can hint at the conditions under which the magma formed and traveled. The habitat itself is, simultaneously, a geological field site of extraordinary richness. Beyond basalt, the floors and lower walls of some Martian lava tubes might preserve sedimentary deposits, materials carried in by water or wind after the tube formed, that could contain evidence of Mars's more recent environmental history. If water entered the tube at any point after its formation, whether as liquid or ice, it may have deposited minerals and potentially preserved organic chemistry in ways that protected it from the surface radiation environment. The search for biosignatures, chemical evidence of past or present life, would be advanced by having scientists living and working in immediate proximity to these deposits, able to conduct detailed, sustained investigation rather than the brief, logistically constrained sampling of a robotic mission. The relationship between the settlers and their geological home would deepen over time in a way that has parallels in human history. Mining communities develop an intimate knowledge of the rock they work in. Agricultural communities learn the particular character of their soil. The people of a lava tube settlement would come to know the specific basalt of their tube in detail, which sections are most stable, which have the best thermal properties, where interesting mineralogy appears in the walls, where the floor is smoothest and where it is rough with ancient flow structures. This knowledge would be practical, aesthetic, and scientific simultaneously. There is something philosophically resonant about this relationship. The rock that shelters the settlement from radiation, that stabilizes its temperature, that provides its raw materials and records its world's history, is the same rock that the settlement's occupants study, learn from, and gradually come to know as intimately as a familiar landscape. The boundary between habitat and subject of study dissolves. The geology is not out there, beyond the walls of the lab. It is the walls of the lab. It is the floor underfoot and the ceiling overhead. It is the world, in the most immediate and encompassing sense. Sleep, within this geological intimacy, takes on a particular quality. To rest surrounded by rock that is billions of years old, that formed in volcanic events predating the existence of complex life on Earth, is to sleep inside deep time. The darkness of the sleeping pod is also the darkness of geology, the darkness that has existed in these tunnels since the lava drained away and left them hollow, an unimaginably long silence interrupted at last by the brief, bright, purposeful noise of human habitation. The mineral world and the human world, in the lava tube settlement, are not separate. They are woven together in a relationship that will only deepen as the settlement grows and as the people inside it come to know their ancient home more fully. That knowledge, accumulating generation by generation, will eventually become the foundation of something that no human civilization has ever had before. A science, a culture, and a way of life rooted entirely in another world. The final shape of that civilization, and the path that leads toward it, is where we arrive now. Part 19. The road ahead, missions, timelines, and the next steps. The civilization described in these pages does not yet exist. No human has set foot on Mars. No rover has descended into a lava tube. No inflatable liner has been pressurized inside an ancient basalt tunnel on the Tharsis Plateau. What exists, at this point in history, is a combination of compelling evidence, serious scientific study, and an accelerating pace of mission planning that is bringing the first human Mars landing closer to plausibility than it has ever been. The steps between now and a functioning lava tube settlement are numerous, and each one is significant. They fall into roughly 3 phases: robotic precursor exploration, initial human surface missions, and the transition to permanent underground habitation. None of these phases has a fixed timeline, and estimates from space agencies and private companies have shifted frequently as technology, funding, and political priorities have changed. But the direction of travel is consistent, and the pace has increased noticeably in recent years. Robotic precursor missions represent the immediate next chapter. Before any human can safely descend into a Martian lava tube, the tubes themselves must be characterized in detail. Orbital imaging has identified pit entrances in several volcanic regions, but what lies below those pits remains largely unknown. Future missions would deploy small robotic explorers, possibly including aerial drones descended from the success of the Ingenuity helicopter on the Perseverance mission, into the pits to map their interiors. These robots would measure temperature, radiation levels, atmospheric composition within the tube, structural stability, and the presence of water ice or other resources. They would build the detailed picture that human mission planners need before committing a crew. Simultaneously, surface precursor missions would work to demonstrate the technologies required for human habitation. The MOXIE experiment on the Perseverance rover demonstrated oxygen production from the Martian atmosphere through electrolysis, a small but symbolically important step toward in-situ resource utilization, the use of Mars's own materials to support human presence. Future missions would scale up these demonstrations, testing water extraction from regolith, solar and nuclear power generation at relevant scales, and the deployment of pressurized habitat prototypes on the surface. Each successful demonstration reduces the uncertainty that makes human mission planning so difficult. Initial human Mars missions, when they come, will almost certainly begin on the surface rather than underground. The first priority will be survival and basic science. Crews will operate from surface habitats, conduct geological surveys, test equipment in the actual Martian environment, and begin the reconnaissance of nearby lava tube entrances. The transition underground might begin with robotic preparation of a tube, deploying the first pressurized liner and verifying its integrity before humans descend. The first humans to enter a Martian lava tube might do so on a brief exploratory excursion, suited and cautious, before the infrastructure for sustained habitation is in place. The transition to permanent underground habitation would follow a logic of gradual commitment. As the lava tube habitat is built out and verified, crew members would begin spending increasing amounts of time underground. Eventually, for most purposes, the underground habitat would become the primary living space, with the surface habitat serving as an airlock and equipment staging area. The psychological and physiological benefits of the underground environment, better sleep, reduced radiation exposure, thermal stability, would reinforce the practical advantages and encourage the shift. Growth beyond the initial settlement would depend on the arrival of subsequent missions carrying additional crew, equipment, and supplies. The 26-month launch window cycle would structure this growth, with each window representing an opportunity to expand the settlement's population and capability. Over a period of decades, What began as a small research outpost could develop into a community of hundreds, with the architecture of the lava tube providing space for expansion that surface construction could not easily match. Technology development on Earth in parallel with these missions would be as important as the missions themselves. Advances in nuclear power systems, closed-loop life support, agricultural efficiency, medical capability, manufacturing from local materials, and communication technology would each expand what a Mars settlement can do and reduce what it depends on from Earth. The relationship between mission planning and technological development is iterative, with each informing and accelerating the other. The scientific return from even the earliest human Mars missions would be extraordinary. Questions about the planet's geological history, its potential for past or present life, and the behavior of physical and biological systems in its specific environment would begin to be answered with a depth and nuance that robotic missions, however capable, cannot fully provide. Human presence, with its flexibility, judgment, and capacity for sustained investigation, would transform Mars science in ways that are difficult to overstate. None of this is easy. None of it is cheap. None of it is without risk, to the individuals who go and to the institutions that send them. But the evidence gathered over decades of robotic exploration, the growing sophistication of our understanding of what Mars offers and what it demands, and the extraordinary architecture of its ancient underground spaces all point in the same direction. The lava tubes of Mars are waiting. The science that explains why they matter is established. The engineering that could make them habitable is within reach. The next steps are being planned, debated, and slowly taken. And somewhere in the future, not yet dated, not yet certain, a light will be switched on inside an ancient basalt tunnel on another world, and a person will look around at the rock and the warmth and the breathing air, and will begin to make it home. Part 20. A Quiet Revolution. What Mars teaches us about sleep, shelter, and being human. There is a particular kind of knowledge that only comes from building something new in a difficult place. It is not the knowledge of theory, though theory is where it begins. It is the knowledge of practice, of discovering what works and what does not in the presence of real consequences. The project of making a home inside a Martian lava tube would generate this kind of knowledge in abundance, and much of it would flow back to Earth in ways that change how we think about our own habitats, our own sleep, and our own relationship to the built environment. The sleep science developed for Mars would be among the most practically transferable bodies of knowledge the settlement produces. The engineering of light environments calibrated precisely to circadian biology, already in development for spaceflight, would find applications in hospitals, schools, office buildings, and homes on Earth. The insight that complete darkness and acoustic isolation are not luxuries but biological requirements would reshape how sleep spaces are designed for the many people on Earth whose sleep is chronically disrupted. The research on circadian alignment in the specific context of an artificial light-dark cycle would deepen our understanding of shift work, jet lag, and the broad range of sleep disorders that affect hundreds of millions of people. The habitat design principles developed for underground Mars living would similarly translate back to Earth in unexpected ways. Evidence-based design for extreme environments, where the stakes of getting it wrong are immediately measurable, generates insights that more forgiving environments obscure. The value of biophilic elements, acoustic management, personal control over the immediate environment, and circadian sensitive lighting has been demonstrated in terrestrial research. but the Mars context would test and refine these principles under conditions of unusual clarity. What keeps people psychologically healthy in a sealed environment beneath Martian rock is, in its essentials, what keeps people healthy in any environment. The Mars version is simply more visible. The psychological research generated by Mars settlement would address questions that are difficult to study on Earth because the conditions cannot be fully replicated. How do small, diverse communities maintain cohesion over years of genuine isolation? How does the absence of natural environment affect human development and identity over generations? What social structures emerge naturally when external authority is distant and the cost of social breakdown is immediate? These are questions with answers that matter far beyond Mars. In the design of remote communities, long-duration naval deployments, polar research programs, and any human context where the conditions of isolation and confinement shape daily life. The relationship to geology that a lava tube settlement would develop, the intimacy with ancient rock, the daily experience of being sheltered by something billions of years old, offers a quieter but genuinely significant reflection on the human need for connection to the natural world. On Earth, that connection is taken for granted, available to anyone who steps outside. On Mars, it would be deliberately cultivated, designed into the habitat, honored in the culture, and studied scientifically. The result might be a more conscious and articulate understanding of what biophilia, the human affinity for natural systems, actually consists of and why it matters. There is also something in the Mars project that speaks to a very old human question. What is a home? Not a shelter, which is merely a structure that keeps danger out, but a home, which is a place with meaning, history, and the specific quality of being where you belong. The first settlers of a Martian lava tube would be making a home in the most demanding and deliberate way imaginable, without inherited landscape, without familiar weather, without the biological web of life that surrounds every home on Earth. They would be constructing meaning from scratch, choosing what to carry from Earth and what to leave behind, inventing traditions for a place that has no human traditions yet. What they would discover, what the research already suggests and what living there would confirm, is that home is made more by the quality of shared life than by the particulars of the physical setting. Good sleep, in a dark and quiet space calibrated to biological need. Shared meals in a warmly lit room. Meaningful work that connects to a larger purpose. The sound of other people going about their lives in the corridors outside. These are the materials of home, and they are available inside a basalt tube on Mars as surely as they are available in a house on a street in any city on Earth. The underground civilization of Mars, if it comes to be, will teach us that the minimum requirements for human flourishing are smaller and more portable than we assumed, and that the desire to explore, to build, and to make a home in difficult places is not a deviation from the human condition but one of its most persistent expressions. The rock has been waiting for a very long time. The darkness inside those ancient tubes is patient and complete. And somewhere in the future, in that darkness, a person will close their eyes at the end of a long day on another world. And the last thing they will feel before sleep comes is the quiet, absolute certainty that they are exactly where they are supposed to be.